Hello, Professor Sargent here with you again. In the previous section, we looked at using the product and quotient rules for radicals. So one might wonder, can we do anything with addition and subtraction? And the truth of the matter is, yes, in some cases. However, it's not quite what people might expect. Remember that a square root has an index of 2. So this square root would be the same as taking what's underneath the square root raised to the 1/2 power. That tells us by the order of operations to do the work in the parentheses first. 25 to the 1/2, i.e. square root of 25, is 5. Whereas if you thought that we could split the square root across the addition, or similarly across subtraction, well then you would be doing the exponents, writing this as 9 to the 1/2 plus 16 to the 1/2. You would do the exponents before the addition. That gives us 3 plus 4 is 7, and 5 is not equal to 7. So these were not equal. In a moment, I'll talk about more generally the things that we can do. But first, an example that is not going to require that information. All right, so we had 4 times the square root of 2, close the parentheses, plus 7 square root of 2. Those were like radicals because they were both square roots, and they both had 2 underneath. That's the decimal approximation that it gives us. Whereas if I put in 11 times the square root of 2, close the parentheses, we're getting the same decimal approximation. These, however, are not like radicals. They are both square roots, but we have a radicand of 5 versus a radicand of 2. Based on what we learned in section 7.3, we cannot do anything to simplify this so that we would have the same radicand. Now this, let's see, can we simplify that? All right, we are going to simplify the cube roots here and then see if we have the same radicand. At least they are both cube roots. All right, so I know that 3 will go into 81, and it took me a little longer to recognize that 3 will go into this as well. 125 times 3 on this one, and 27 times 3 on the second one. Then 125 is a perfect cube, as is 27. I'm going to use the product rule to split this up and simplify the parts with the perfect cube underneath. Cube root of 125 is 5. And the cube root of 27 is 3. So notice that initially on that first term, we had that multiplied by 6. And so the 5 that we brought out from the cube root, we've got to multiply that. 30 cube root of 3 plus 3 cube root of 3. They're both cube roots with the same radicand of 3. So we should be able to combine that as 33 cube roots of 3. You can do the same kind of check on the calculator. Let me bring that back up. There we go. All right, so 6 times the cube roots of 375, 375, 375, come on, plus outside of that, 3 times 3, the cube roots of 81, and that's our decimal approximation. I want to compare that to the decimal approximation for 33 times the cube roots of 3. Oh, I forgot to type the index. 3 cube roots of 3. And it's looking the same. When I go to type that in, not only are they coming out the same, but also I know I've simplified it the most that I can, because 3 is not a perfect cube, and the only perfect cube that goes into it is 1. There we go. All right, what about this one? 5 times the square root of 75 minus the square root of 147 plus the 7 times square root of 192. We can see that the 75 is 25 times 3, where 25 is the largest perfect square to go into 75. What I would hope is that these others are also some perfect square times 3. I can't guarantee that, but in this case, 49 times 3 is 147. 49 is a perfect square. And 192, 3 does go into that as well. It goes in, let's see here, 64 times. And 64 is a perfect square. So applying the product rule, taking the square roots of the perfect square parts, and then if I had a coefficient in front in one of the terms, do this multiplication, do this one as well, and 25 minus 7 is 18. We do have like radicands, both square roots, both with like radicals, both with square roots, and the radicand is 3. And then adding 18 plus 56, I'm getting 74 square root of 3. So let's see if they get the same thing. 74, 74 square roots of 3. And it's good. Looking at square root of 75x minus square root of 48x. As they are currently written, although these are both under square roots, we have different radicands, so they are not like radicals. However, 75 is 25 times 3, and 48 is 16 times 3. The power of x only being to the first power, that's less than the index. So I'm not going to be able to do anything simplifying these radicals that involves the variable. Use the product rule. And take the square root of the 25 and the 16. It's going to give us 4 times the square root of 3x. Sorry, 5 minus the square root of 3x minus 4 times square root of 3x. And 5 minus 4 is 1. So our final answer is just square root of 3x. We have something similar here. They're both cube roots, but we have different radicands. And also, the power of the m is just the first power, which is less than the index of 3. Well, let's see if we can simplify the numbers and see if we're looking at like radicands after all. 27 and 8 are both perfect cubes. So I'm splitting those off under separate cube roots from the m's, still under cube roots. Cube root of 27 is 3. We already had a 3 multiplied to that radical. And cube roots of 8 is 2. That was already multiplied by a 3. So doing that multiplication, we've got 9 minus the cube roots of, 9 times the cube root of m, minus 6 times the cube root of m. Now we're looking at like radicals, and we'd say that that is 9 minus 6 is 3. So 3 times cube root of m for our final answer. Both cube roots this time. The radicands are different. On the first one, a power of 1 for the x and a power of 2 for y. Those are both too low compared to the index of 3. But we do have this cube root of 125 to simplify that in the second one. And also, we've got the same power of y, but we have x to the fourth on this one, which is larger than the index. So what I'm going to do is, since 125 is already a perfect cube, and x to the fourth can be written as x cubed times x to the first, break up, factorize the second radicand, apply the product rule. So we're taking the cube root of 125, which is 5 cubed, and the cube root of x cubed. Oh, let's see here. Oh, we still have that x there. Okay, so 19x times cube root of xy squared minus 4 times 5 times x times cube root of xy squared. It could be 19x cube root of xy squared minus 20x cube root of xy squared. Those two radicands are both xy squared. They're both under cube roots, so these are like radicals. 19x minus 20x is negative 1x, or just negative x, and that would be in front of cube root of xy squared. On this one, we've got a pretty large number under a fourth root. We have m cubed under both of those fourth roots. maybe the 5 goes into 1280. Let's see here. Maybe the 5 goes into 1280. 10, another 28, goes in 5 times. 28 minus 25 is 30, 256. Well, it turns out 256 is a power of 2 and some other numbers as well. Let's see here. Can keep dividing 2 into that. Running out of space, but we know 16 is 2 to the 4th. All right, so 1280. Got 2 to the 4th here and another 4 there. I'm going to write this a different way though. 2 to the 4th is 16, which is 4 squared. 4 squared times 4 squared is 4 to the 4th. 4 to the 4th is 1,000. 4 to the 4th is 256, and 256 times 5 is 1280. All right, so are we going to make use of that? 4 to the 4th times 5. Because the power of m is below the index, I'm not going to be able to do anything there. Apply the product rule on the first one. And since 4 is already positive, we don't have to worry about absolute values. So the 4th root and the 4th power are canceling out. That's 9 times 4 times the 4th root of 5m cubed plus 11 times the 4th root of 5m cubed. 36 when we multiply. And now we're looking at both of them are 4th roots with the same radicand. These are like radicals. We'll add the 36 plus the 1 to get 47 times the 4th roots of 5m cubed. Although we have different indices here, we're not going to be able to combine, but we may be able to simplify. 8 has its largest perfect square factor is 4. The power of the x is too low. 1 is less than the index of 2. But I can write y cubed as y squared times 1. Sorry, y squared times y to the first. Similarly, 16 has as its largest perfect cube factor 8. Sorry, I forgot to write the 2 there. 8 is 4 times 2. 16 is 8 times 2. The index is too low, 1 versus 3. Well, y to the 4th, that's 1 higher than the index. Split that up as y cubed times y to the first. And applying the product rule. Now we can take the square root of the 4, take the square root of y squared, take the cube root of 2 and the cube roots of y cubed. Keep in mind though, these were not like radicals right from the start because of the different indices. So although we could simplify, we cannot do anything to add terms here. By the way, I should have mentioned this earlier, but we're assuming that the values that go in for the variables are positive, so that we don't have to worry about writing anything to do with absolute values when we have even indices. Here, the radical parts that we have are like radicals because they're both square roots and the radicands are both 5. So I can subtract 3/4 minus 1/8. That would be in front of square root of 5. Get a common denominator. Multiply top and bottom here by 2 to get 6/8 minus 1/8. And subtract the numerators. I've got 5/8 in front of square root of 5. On this one, there's a lot of approaches we could take. However, I notice that when I reduce the second fraction underneath the radical, that gives me a 2 under a square root that I cannot simplify. 2 is not a perfect square, and the only perfect square that goes into it is 1. So what about, let's see here. On this one though, split up the square root with a quotient rule. On one hand, square root of 16 is 4. With the numerator, 18 is not a perfect square, but it is 9 times 2. 9 is the largest perfect square that will go into 18. And now we're starting to see something similar here. So apply the product rule up in the numerator. Take the square root of the 9. Get a common denominator. That was just a 1 square root of 2 on that. And finally, we've got the same denominator. We've got like radicands. So add across the numerators. 7 square root of 2 all over 4. Hopefully, on that last one written on the board, there is one more thing I'm going to show after that, which is on MyLab. Hopefully you notice the similarity with the first square root in both of those. If I apply the quotient rule in the opposite direction on this, here I'd split up square root of 18 over square root of 16, and then simplified. Square root of 16 was 4. That's where we got that denominator from. And I had to break up the 18 as 9 times 2 while it was still under the square root. Here, if I go the other direction, put the square roots back together, that reduces to the same thing that we had previously. And from there, the work is going to proceed the same way as it did here to get 7 square root of 2 over 4. So the reason I included this was, yes, sometimes to simplify things, we want to use the quotient rule to break things up. Other times, we want to go the other direction. Put it back together, simplify inside. That might give us the most simple version to look at. One more thing to look at on MyLab in just a moment. We're asked for what is the perimeter of the computer graphic shown here, and we've got measurements of all 4 sides of a rectangle. I've copied it over on the board. Remember that the perimeter of a rectangle is twice the length plus twice the width. And that's because these two should be the same. These two should be the same. I'm going to check that by simplifying wherever I can. 20 as before, as its largest perfect square to go into it, 5 times, and then apply the product rule. Take the square root of the 4. Leave the 5 underneath the square root. We already had 4 times the square root of 20, so that's going to be 4 times the 2 square root of 5, or 8 square root of 5. Going backwards, 8 squared is 64. 64 times 5 is 320. 2 squared is 4. 4 times 80 is 320. So I should be able to simplify this and get the same thing. 16 times 5 equals 80. Apply the product rule, take the square root of the 16, and we also get 8 squared of 5. The square root of 48, the largest perfect square to go into 48 is 16, 3 times. Apply the product rule. Square root of 16 is 4. I can't do anything with 3, just like I could not with the 5, because the largest perfect square that goes into either one of those is 1, which won't help us simplify anything. So going backwards here, 2 times the square root of 12. If I were to put that 2 back in, 2 squared is 4. I would have 4 times 12, or 48, underneath the square root. Double checking. The largest perfect square to go into 12 is 4. It goes in 3 times. So we'll have 2 times 2 squared of 3, which is 4 squared of 3, just like we had here. So I'm going to take 2 times the 8 squared of 5 for my length. We're seeing it here and here. And then here we're seeing 4 squared of 3 for the width. Double that. It gives me 16 squared of 5 plus 8 squared of 3. And that's as far as I can go if we're to leave it in exact form, because although both of those are underneath a square root, the index is the same, but the radicands are different. So those are not like radicals. Let's see if they take that answer, 16 squared of 5 plus 8 squared of 3. And they also want how that's measured. Well, this is perimeter. We're just adding up inches plus inches is more inches. So not any of the other choices. That would be talking about volume or area. And it's good. That's all I have for now. So hope it helps, and I'll see you in class.